Yeah, I'll get this sign-in sheet going around. So I think we didn't do it last time, right? So just, or maybe we did, who cares? Just to sign in for the 9th, please, and just skip that column that has the purple in it. Okay, so it's that, and then you have to pay real close attention to this next part. This is 1, this is 2. It has an open circle here, and then it comes down, another dot here, comes down like this. This is the 0.20. This is the 0.00. That's it. That's the whole thing. Here's the picture. They want you to come up with the piecewise function that draws this. So do you understand what it wants? It wants f of x equals, and then a brace, and then the 2 or 3 pieces, however many pieces it's going to take to draw this. So how many pieces do you see? 2, this one, and then this one, right? So let's talk about this piece right here. This is a line, right? This is a line. What is the slope of this line? The slope, -1. Everyone agree? So this right here has a slope of -1. Do you know where it hits the y-axis? At 0, so it has a y-intercept of 0. Now remember, when you're talking about lines, equations of lines, one form of an equation of a line is y equals mx plus b, where m is the slope and b is the y-intercept, right? Y'all follow? So if I plug in m is -1 and b is 0, that will draw this line, right? But I have to restrict it because it doesn't keep going, right? It doesn't keep going. It stops here at 0. So I'm going to put here, what would I get here? If I replace this, get -1 in front of x and -x plus 0, just -x, right? So y is -x. So this will be -x if, what though? Your x value is what?
X is less than or equal to 0.
Less than 0 or equal, because what happens at 0? You have a solid dot right down there. X is less than or equal to 0. All right? No questions? Then we switch. Now we switch to a different piecewise function, which is this one. What's the slope of this line? Same thing again, right? -1. But our y-intercept is different. Where does it hit the y-axis? 2. Now it actually doesn't hit because there's an open hole here, but that's where it would hit if it continued. So b would be 2. So the equation would be -x plus 2, wouldn't it? If I were to put it in this form. So that should be the second piece. -x plus 2. But this is only if x is what? Bigger than 0.
Greater than 0, but less than or equal to 2.
Less than or equal to 2. So x must be between 2 but bigger than 0. I'm just going to put a comma here instead of if. Does that make sense?
Could you put that, explain that again?
Okay, yeah. So you're okay with this? Okay. So where does the graph stop? Because they didn't have an arrow, the biggest x value we could have is 2. And then so x has to be less than or equal to 2. But it also has to be greater than 0, and it can't actually be 0 because then that would be filled in solid. So I have to say strictly greater than 0. Make more sense? Okay. Yep. So that would be it right there. That's the piecewise function. I'll entertain one more if anyone else has a question. Same page. Everybody signed in? or I'm sorry, same section is what I meant to say. 55. Oh, a word problem. Okay, let's take a look at 50. I'm not going to write 55 word for word up here. I'm assuming all of you own a book. You may not have it, but I'll read it. Cost of transporting goods. A trucking company transports goods between Chicago and New York, a distance of 960 miles. So Chicago and New York. $960. I'm just putting information down visually for myself here. I've never done this problem, so let's see how it goes. The company's policy is to charge for each pound, what is that? For each pound, this per mile. How much is that? 50 cents, right? That's 50 cents? Okay, so they're going to charge for each pound that much per mile for first 100 miles. And I'm going to put here per pound. 50 cents per mile for the first 100 miles per pound. Then 40 cents per mile for the next 300 miles. 40 cents per mile for the next 300 miles, right? And that's per pound again. And then 25 cents per pound or per mile for next 400 miles. There is no charge for the remaining 160. So 0 for the remaining 160 miles. Okay. First, graph the relationship between the cost of transportation in dollars and mileage over the entire 960-mile route. So they want us to graph a cost function, basically, that represents how much we're going to pay for whatever miles we go for this entire trip. This is going to maybe look like a piecewise function. We'll see. Everyone understand the problem, though? Okay, so that's what I've got. So let me draw here. Let me make sure I read this carefully. Graph the relationship between the cost of transportation in dollars and the mileage over the entire 960-mile trip. So we're going to say miles here, and this is going to be cost. We know the total mileage is 960, right? What's up? Do you have a question, or?
You just came back in and I was explaining what
Oh, okay.
you're doing.
Okay. So how much is it going to cost us? And see, here's the thing. We don't know how many pounds we're shipping right now, right? This is all per pound, right? So let's just say, for the sake of just getting our heads around the problem, that we're shipping 1 pound. So that way this will be easy math to begin with. How much is it going to cost us for the first 100 miles? 50 cents per mile. So, and we're going 100 miles. So how much is that going to cost me?
$50.
$50? How are you getting it?
Multiply 0.5 times 100.
So it moves it over twice. So you get 50, right? So it's going to cost us $50. So I'm going to put here $50 for that first 100 miles, right? That's what it's going to be. Yes? Now, if we go short, also I should not draw solid because that's not what it is, right? As far as if I go 50 miles, is it going to cost me $50? No, right? How much is it going to cost me to go the next 300 miles? So that'd be 100 to 400. So how much am I going to pay to go this next?
120.
So you're doing 300 times this,
Yeah, so
which would be
120 plus the initial 50, so
120.
70 total.
So how do we want to do this? Do we want to, when we get to 400 miles, we know that we're going to pay this much more, but we already paid 50. So you want to tack it on top?
Yeah.
So it'll be the 50 we started with, which would be here, but add 120,
Yeah,
which would put us where?
170.
170? Understand? We good? And then what? 400 miles. The next 400 miles would put us out at what? 800? And how much will we pay for that? 400 times this would be 100 bucks. So now I'm off my chart because I'm going to take the 170 we already paid. I'm going to add to that, so we're going to be up at what? 270. And then for the remainder of the trip, it's free. So at the end of the trip, I'll be here at what? Still 270? So if I ship 1 pound, that's how much it's going to cost me. Agreed? What if I ship X pounds? 270 times X. Because this, instead of being 50, would be 50 per pound, wouldn't it? So if I just ship 2 pounds, this would now be 100. If I ship 3 pounds, this would be 150, right? So everything just gets multiplied by X. So at the end of the trip, at the end of it all, right, you should have 270X is the total cost. Do you agree? For X pounds. That's what it would be. Now, the next part says find the cost as a function of mileage, which is what we have here, for hauls between 100 and 400 miles. So now we're saying instead of going all the way from Chicago to New York, what if you only are going to go somewhere between 100 to 400 miles? Can you tell me how much you're going to pay? I mean, we know if we go the whole way how much it's going to be, right? 270 times X. But what if somewhere in here we're stopping and that's all we're going? Can we find the cost as a function of mileage? I'm going to start this kind of over.
Basically trying to find the slope of the line, wouldn't it?
Well, maybe that's one way we can interpret it. If we're going to go between 100 and 400 miles, right? If that's what it says for part B. The cost if we're between 100 and 400. So if you're only going to look in here, this is very tricky, so let's try and pay attention, all right? We definitely are going to go the first 100, right? So the first 100, how much are we going to pay?
50X.
50, right? Just 50. Well, if we're going to say X is the pounds. Let's again, this is miles. This is cost, right? And let's let miles in our cost function, let's let it be M. So we're going to say like the cost is a function of miles. We know for sure if we're going to go between 100 and 400 miles, so I'm going to put a domain restriction here. M is between 100 and 400 miles, then my cost is going to be this. Definitely the first 100 miles at 50 cents per mile, which we said was $50. That's going to be a fixed cost, right? That's never going to change if I go at least 100 miles. So it's going to be 50 plus, now this is the part that's tricky. Let's say I only go 200 miles. Let's say that's how far I went. How much am I going to pay for this piece? How are you getting 40?
Just multiplying that 0.4 cost per pound by 100.
By 100, right?
Yeah.
By 100? Because that's how much further you've gone. If this was now, instead of 200, if we had gone, let's say 250, then it would be 0.40 times 250? Times 150. See, this is the part that you have to account for. M is how many miles you've gone total, right? So isn't M 250?
Yeah.
But to get how much it's going to cost in here, I don't want to multiply 0.4 by M, right? I want to multiply by what? M
Minus 100.
take away 100. So watch the way I'm going to write this here. It's going to be 0.40. I'm going to run out of room. Let me move this over. The cost as a function of M is going to be the 50 plus the 40 cents, right? Times, not M, but M minus 100. So now if you plug in 250, right? You're going to spend the 50 bucks for the first 100 miles there, and then you're only going to pay 150 miles, which is this, right? At the 40 cents per mile. Yeah? Now distribute. Here to here, here to here. And I'm going to put the 0.40 M out front. And what's this times 100? Minus, or negative 100? Minus 40, which is going to then add to 50 and become 10. This is it right here. If you go between 100 and 400 miles, then all you have to do is plug M into this, and that'll give you your cost for the trip.
And then for C, pretty much do the same thing.
Pardon? And for C, the difference is that you're going to have a fixed cost for this and this. So your constant's going to be different. And then this last piece, if this right here is M, then it's going to be what? M minus 400.
Minus 100.
Nope. No, because this 400 accounts for this 100 already, right? So minus 400. Hope that makes sense. Part C, I'll tell you what the answer for part C is. For part C, I'll let you do it on your own. It's 70 plus 0.25x. Or you could write it the other way around. Questions? All right, let's get to today's stuff. See, these are the things that I was trying to tell you, last class. You got to be careful in this class because that problem is fair game on a test because it's in your homework. So if you have any questions over these homework assignments, you need to make sure you're getting with me, getting with tutoring lab. Okay, you don't want to be like, well, you never did anything like this in class. Well, it's on your homework so that you have the opportunity to ask questions, clarify the concepts. And if, the thing is, I'm not going to go outside of your homework or outside of the lecture and pick problems I never assigned you or never showed you. I won't go outside of that. But if I'm going to promise you I'm not going outside of it, then you're accountable for the stuff that is presented. Understand? Okay. All right. We're going to move on. We were looking at piecewise functions last time, right? We started talking about it a little bit, and I just thought I'd show you this one example just to make sure everybody kind of understands what's going on. I think I'm going to kill the lights a little bit because it's hard to pick up. There we go. So here's the piecewise function, negative 3x if x is less than or just less than negative 1. 0 if x is equal to negative 1, and 2x squared plus 1 if x is greater than negative 1. So you have 3 pieces, right? And so what I've done is I've graphed all 3, and I've color-coded them so you can see them, right? You have y equals negative 3x, which looks like this. You have y equals 0, constant 0 function. And then you have that parabola, y equals 2x squared plus 1 right there. But because we have domain restrictions, this negative 3x is only drawn to the left of x is negative 1. So if I go ahead and, I think this is the one. See, this is x is negative 1, right? To the left of that, I only want to draw this guy right there. So I only want to draw that piece, right? And then in the second interval, which is x equals negative 1, I want 0. So that's actually going to be at x is 0. Where the heck is it? Oh, at x is negative 1, pardon me. At x is negative 1, it's 0. So here's x is negative 1. And I just want to put a dot right here. That's all I want to do. So that's this right there. And then on the second, the last piece right here, which is the parabola, is this green region. I want to graph that. And then I'm going to take all this shit out of here because it's just confusing. I think I've got it all there. That's the graph of the piecewise function. So it's a line to the left of negative 1. Until you get here, then you have to jump down, put a dot. Then you go back up here, and you draw the rest of your parabola the rest of the way. See how that all fits together? Okay. So if I were to give you a piecewise function, I would expect that you could graph it. And if I give you the graph, it would be more like the one that was asked, where there are lines, because those are easy to pick up, like what the slopes are and things like that, and then you paste them together. So any questions on this?
I have a question.
Yes?
Where the blue and the green line meet, you have an open circle?
Yes.
Is that because y equals 0 on the bottom?
That is because this line is not defined at negative 1.
Okay.
See the greater than, not equal, and then this one's greater than, not equal. So the question is, what's happening at negative 1? Well, at negative 1, we want to be 0. So that's why when you get to negative 1, you don't fill that in. You actually come down here and plug in at 0, you put a dot. Okay. We got a lot more graph stuff to look at. Where's the next one? All right. So 3.5 is the next section. And this is graphing techniques. So if you recall last class, what I did was I introduced the idea of this toolbox of functions that we all should know. Right, we should be able to just, oh yeah, sure, the square root of x looks like this. Absolute value of x looks like this, right? We have all these functions in our mind. Now what we're going to do is we're going to use basic properties to be able to create transformations of those graphs. And the first thing we're going to look at are vertical and horizontal shifting. So let's see how this reads. If y is some function of x, so notice, I'll just highlight this. If y is some function of x, and you know what the graph of f looks like. So f is something you know. If you add a number to it, what is it going to do to the graph? It makes it go up. If you subtract a number, what's going to happen? It's going to go down. What if you add, I put in here, you add h. What's the difference between this one, adding h like that, and adding k like that? What's the difference between those two? It's in the parentheses. The h is in the parentheses, and the k is outside. So let me show you an example of the difference of those two. I'm going to ask everyone to remember what this function is. What does that look like? It's your v, right? With the sharp corner? Yeah? We all know we can just draw it real quick if we needed to. All right, compare that. I'm going to say f, I'm going to put 2 down here, just because it's a different function. It's not the same thing. Plus 2. And then f3 down here which is going to be this. Okay? So the first function up here is comes from our library, right? Or the toolbox, right? We know what that one looks like. This one, the 2 is being added outside the absolute value. So this should move that picture that we know, it should move it up 2, shouldn't it? And this right here, because the 2 is being added inside the function, right? That's inside the absolute value. This should have the effect of doing what? Left 2. Now, your instinct, adding 2 up 2 makes sense, right? Because positive is up. When you add 2 inside, your instinct would probably make you think adding is positive to the right, this way. But it's actually opposite. All right? So when you have shifts that are horizontal, they're opposite of what you think. Vertical shifting is what you think, what naturally, positive up, negative down. Right? So let's see how quickly I could graph these. That's F, isn't it? Okay, move up 2, take this whole picture, move every point up 2, and it would draw the same picture like that. That's F1, or sorry, that's F2. That's this one, isn't it? And then this one would be the original picture moved left 2. So, pardon? It's not wider, no, because all we're doing is moving it, translating it. When we do translations, it's just up, down, left, right. Nothing is going to widen. Not yet. We're about to do that. So it's just going to be like this. This is F3. Understand? Vertical and horizontal shifting is the most basic type of shifting that you can have, transformation. But they're useful. All right. And if this were a -2, of course, we would go to the right 2. If this were -2, we go down 2. What's nice about this is that this works for any function that you know what it looks like. So when you get to pre-cal and you're talking about sine curves and cosine curves, this all applies. You can move them around doing the same thing. All right, now we have what's called stretching and compressing. So this gets a little weird. So let me do this with an example. I'm going to show you this same. Let's just stick with this one. This is our library function, and we're going to compare a couple. First, I'm going to say f sub 2 of x. Let's do the first one. We're going to multiply by a number in front. A, you see the number in front of the function? And that a is going to be bigger than 1. So how about I put like 2 absolute value of x. And then the next part says, what if I take a number in front that's between 0 and 1? So what about 1/2? It's between 0 and 1. And then the third one, well, we'll get to the third one in a second. Let's just look at those two. So you start out with your library function, which is this absolute value function right here. All this does, this one, is doubles all your answers. These are your y outputs, aren't they? You plug in an x, it spits out this for y. Now I'm supposed to double them. So what is the y value right here? What is your y value on the original function right here? What's the y value? 0. What's 2 times 0? Still 0. Okay, what's the absolute value function, this one, at 1? It's 1, right? Now double it. It's going to be 2. So instead of being here at 1, it's going to be up here at 2. And the one out here was 2, right? You plug in 2, you get 2, but now you double it, you're up at 4. So what this does is this, right? And if you go to the other side, it's going to be the same thing, like this. This is f sub 2. Do y'all see that? So what do we call this? It depends on how you want to look at it, actually. Someone could say that I've stretched it vertically, that I've taken these 2 points, like these 2 arrows, and I've pulled them up, which made the effect of doing this, right? So I've stretched it out vertically. Someone else may say I've compressed it horizontally. I've taken this and I've smashed these in and made it horizontally compressed. Those are pretty much the same. Vertical stretch is basically a horizontal compression. Understand?
But technically, that would be a stretch. I guess that's what the book would say.
I'm not sure what, let's see if they identify which one. Shifted. Vertically stretched is what they call it. Yeah. So that's where I said the first way I said you could stretch it out. Now, if the number in front is bigger than 1. If the number in front is between 0 and 1, what does it do? It's the opposite, right? Like if this was supposed to be a 1, now it's half of that, so we're here. If this was supposed to be 2, now it's 1, so now we're here. So it has the effect of drawing this.
So it's a vertical compression / horizontal
Stretch, yeah. This would be like you're taking it vertically and compressing it, which smashes the edges down. Understand that? These are hard for me to test you on because it's hard for me to see vertical stretches and compression. It's hard for me to see that in pictures. But you just need to understand, you need to get the idea of what's happening. All right. Now, what if the number that you have is inside? So let me show you those. I'll put those here. F4. So what if you have in here 2x like that? Well, let me have the original one up here. And get all these others out of here. I'll just draw a whole new one. Okay, here's the original one. Like this. So what does doubling inside do? Double.
Like the X and Y, should they both be double?
I don't know. Would they? What do you think? Just try one. Give me a value of x right now.
Yep.
You want 5? Can you be a little closer?
Okay, 2.
Okay.
1.
All right. Let's go. Let's start it in the middle. Why don't we start there? Plug in 0. What do you get? 0. So we're still here, aren't we? So this doesn't have the effect of moving it up, down, left, or right. But now watch. When we plug in 1 now, this is actually what? 2. So when I plug in 1, I'm actually, instead of being up at 1, I'm actually up at what? 2. Now what happens if I plug in 2? When I plug in 2, I'm actually at 4. Right, absolute value of 2 times 2 is 4, so I'm up here at 4. Instead of 2, yes? What about the negatives? What happens if I plug in -1? So -1, what happens? This becomes -2, absolute value is 2. So instead of being -1, 1, we're at -1, 2. And then if you plug in -2, you'll be at where? -4, absolute value. So you'll be, instead of 2, you'll be up here at 4. What happened? What does that look like to you?
Vertical stretch.
Looks like a vertical stretch again, right? Or a horizontal compression.
It looks like the same thing as the 2.
It looks like this one, right? Doesn't it? It looks like this one. In fact, they're identical in this case because of the function itself. But
because there's nothing added or subtracted at the end. Right?
you could pop this 2 out of the absolute value with the property of absolute values, but the idea is this. If you put a number in here in front that's bigger than 1, it's going to do a horizontal compression, which is almost like a vertical stretch. Now, what if the number in front is smaller than 1, but bigger than 0? What do you think there? It's going to be, do it this way. Horizontal stretch. All right, so let's plug in a number that we know will get a nice value out of here. How about 0? Okay, 0, we're here again, yay, we're still at the origin. But now let's plug in a nice number here. How about 2? When we plug in 2, what's half of 2? 1. So when I go out to 2, instead of going up to 2, I'm going to actually only go up to 1. And the next nice number that I can plug in here would be like 4. Half of 4 is 2. So when I go out to 4, instead of being up here at 4, I'm actually only at 2. Make sense? So we get this right here, like this. And we go the same thing the other way. So that one, this is actually this one. They don't match by color here. That one was a horizontal stretch, which you could also almost look at as a vertical compression. Right? Okay, let's talk about reflections. If you put a negative number in front of a function, we're going to stick with this one. If you put a negative in front of a function, it has the effect of reflecting it over which axes? It says it up there. X-axis. Let's see if that makes any sense to you. If this is the original function right here, then to say that it's reflected over the x-axis means that it would look like this, right? And that's because everything that used to be positive, every y value that used to be positive, is now negative, isn't it? Every positive y value is now negative. Every positive is negative. 0 is neither positive nor negative, so it doesn't move. So do y'all see that? Everything just flips. Now, if you happen to have a function that was down here already, like this, what's a toolbox function that would have both positive and negative parts to it? X cubed, good. X cubed looks like this, that's x cubed. Negative x cubed, so negative in front of this, would look like that, wouldn't it? Because it would bring this part that was negative up to be positive. It would take the part that's positive and take it and flip it down over the x-axis to become negative. So that's a reflection over the x-axis also. We good? Yes?
So on X cube, we do like vertical compression and stuff, so I guess it would just kind of get tighter in or...
What would happen if we tried to graph? You want to just look at maybe like 10 x cubed? What that does is it takes every value and multiplies by 10. So what I like to do is imagine that this, whatever this value was, let's just say it was, I don't know, y, right? It's now 10y, which is way up here. So it's like taking that point and dragging it up here, and all the other pieces come with you. And so it makes it much steeper, right? So it's stretched that out. Do you see why you can look at it as a stretch? And then this piece over here dives down faster. But see, it's hard to draw that unless you have really like graph paper and or you use a computer. Yeah. Well, I think I have this all here. I can mess with it myself. So like, you want to see x cubed? There it is. Let me move it around. There it is. There we go. There's x cubed, right? And then if I want to, I can stretch it out in front. Let's see. Just watch it. Let me make it a little smaller. There. If I stretch it, see it? Now the original x cubed is the red one. You see it? That's the idea. I have this set up so you could do all the different basic functions. So there's the cube root of x, right? And so what if I put this, let's talk about what this would be. If I asked you to sketch this, so this is an example. I want you to sketch, why don't you take a minute to try and do it yourself? I want you to sketch f of x equals 2 cube root of x minus 2 minus 3. I'm going to see if you can sketch that. This should not be a 20-minute problem. This should be about a 3-minute problem at the most. And if you're having trouble sketching it, at least do this. List the transformations. In other words, tell me, even if you can't draw it, tell me what sorts of things are going to happen. Okay, like it's going to move this way by this much, and try and give me verbally or a list describing what's going to happen. If anyone thinks they have it, let me know. I'll come by and take a look. Think you got something? It's all right. So, right 2, down 3, vertical stretch. Yeah, okay. I'll have to verify with the picture, but I think that's going to work. Who else?
So what this is, to go right twice, compress it by 2.
If you multiply by 2 out front, it's going to do a vertical stretch. Let's make everything taller. Because vertical compression would smash everything down. Okay?
But what about everything else? Was it right about everything else?
Yes, everything else is great. Yeah. Vertical. Down 3. Yeah, that looks right. Okay. You got some? I think most people are getting it. Okay. Well, I think most of you are getting it. So let's talk about these transformations. First of all, what's the toolbox function? Everyone has to recognize this is the cube root function, which we know what that looks like, right? It's just a matter of all the different things. So let's list them out. You tell me. Just let's have volunteer. Go ahead. Give me one of the transformations.
You had -3, thinking it shifts down 3.
Okay, down 3. Anybody oppose this? Down 3? Everyone's on board?
With the -2 that's inside the cube root, that would mean you would move to the right 2.
Right 2? Anyone disagree with that? Okay, you want to give me the next one? Go ahead.
And it's going to multiply all of the outputs by 2.
Okay,
2
so
out in front.
that would be, what kind of transformation is that? Horizontal compression or vertical stretch, whichever way you want to look at it.
I think it would be easiest to just look at which way it's stretching.
It's, it's different for everyone. And no matter how many times I've covered this section, everyone sees it kind of a different way. So vertical stretch by a factor of 2. So we have three basic things that happened here, right? Everyone's on board with that? Here's my question to you. Does the order in which you do these transformations matter?
Yes. Maybe.
Yes, maybe? What do you think? Let's take a vote. How many of you think the order that we do these matters? How many of you think that the order we do them doesn't matter? And anybody not care? Okay. Okay, so it looks like we've got some different opinions on this.
I mean, like, if you were asked to do like a certain set of like transformations in a specific order, then they would matter. But if we're just trying to figure out like what different transformations are done in just one problem that already has in place, then
What I'm getting at is if everyone agrees these are the transformations that appear in this problem, then if I start to take that picture and start moving it around using this, does it matter if I do the down 3 first, then the right 2, then the stretch, or can I do the stretch, then the right 2, then the down, or can I do the right, then the stretch, then the... Does it matter?
Right now, it doesn't look like it does matter.
Most of the time, it doesn't, but sometimes it does. And because of that, we have to use order of operations to be safe. Now, do you remember order of operations? You do parentheses, exponents, multiplication, division from left to right, addition, subtraction from left to right. Yes? So what you want to do is look at this. And when I say order of operations, it's a little confusing because you're like, what do you mean? There's this. I can't evaluate this because I don't know what x is, right? But let's imagine that you were x. If you were x, the first thing that would happen would be this, right? Which means you're going to do this first. I'm going to list these in the correct order to do them in. After you do this, what comes next? The cube root. The cube root is going to give you your basic shape, which we knew from the beginning of the problem, right? We knew what this toolbox function was. So I'm not going to list that as like the next step. But after this, are we going to do the times 2, because this is multiplication, or are we going to subtract 3? We're going to do multiplication before subtraction, aren't we? So the next thing would be a stretch, and then finally followed by the down 3. And I'll try and give you an example of one where if you do it in a different order, it will give you a completely different graph. Right? I'll give you an example after I do this one. Okay, so here I go to sketch this. If I'm sketching this on a test, here's what I would do. I would start out by very lightly with my pencil drawing cube root of x. That way my instructor knows. And by the way, on the test, I will ask you, what's the toolbox function or what's the library function? I will ask you to list out the transformations in correct order. Then I will ask you to draw me the picture. So I would like to see that toolbox function in there. And then you can just give me your final answer. But it's nice to see like maybe one point get moved around here. So first thing I'm going to do is write 2. Right? That's where I am now. And then I stretch. Now the stretching is the next thing to happen, but it's hard to draw it right now. If I were to stretch it, it would probably look more like this now. Would you agree with that? I've taken this picture and I've stretched it out like this. So there, I moved it to the right 2 and I've stretched it. And now, down 3. So take this dotted picture and just move it down 3. 1, 2, 3, and that puts you right here. And now draw it nice and solid like that. That would be good enough on the test.
When you want us to do the stretching or compressing, does it need to be very accurate?
It does not need to be accurate because the whole idea of this is to be able to quickly sketch. And if we're sitting here taking our time to like draw points and then it defeats kind of the purpose. Yes?
Are you going to want us to show that order of operations in our work in sketching them?
No, only when I ask you to list them. I'll say list them in the proper order.
So if you do not ask us to list it, then we can just do a quick dotted sketch of the toolbox function and then our
Final picture, yes. Okay, so let me try and give you one that the order will matter, okay? All right, what's the toolbox function here? I'm using the word toolbox and library the same, right? Because in different books they call them toolbox functions or library of functions. And
Square would be a problem.
okay, so it'd be the squaring function, right? So the toolbox is x squared, which we call the squaring. If you write x squared, that's fine. If you write squaring, that's fine. All right, let's list out the transformations in order. So what's first?
Left
Left 3?
is directly on the
Because that's inside here with the x, right? Adding 3 sides. So left 3. Next thing.
reflection over the x-axis.
That negative is like a -1 sitting out front. Negative's in front of the function, flips it over the x-axis. Reflect over x-axis. Okay?
Move it down 5.
Down 5. That would be it. That would be the order. Okay? So let me try and draw this real quick. So I start out with the squaring function, which is this. I move it to the left 3, which is this. I reflect it over the x-axis, which is pivot the whole thing downward. And finally, down 5. So this whole picture comes down 1, 2, 3, 4, 5. Here we go. And it goes down like that. Let's try it a different order and see if we get the same answer. So I'm going to do it intentionally to make it mess up, all right? I'm going to do this first. I'm going to go down 5 first. Okay? That means I start with this, right, and go down 5. 1, 2, 3, 4, 5. I'd be right here. I'd be up like this, right? Now what do you want me to do? I'll let you choose the next two.
Left 3.
You want me to go left 3? Okay, 1, 2, 3. So now I'm here, right? Now what? Flip it over the x-axis. Here's the x-axis. It flips all the way over like this and comes up here like this. Do you see that? It doesn't flip over this. That's not the x-axis. The x-axis, right? This point right here has to go right there. You see that? So it's dangerous.
So technically, wouldn't it be? Oh yeah.
Like if this y value, right, is -5, now it's going to become +5.
So if you started out like reflecting it over the x-axis first,
If you reflected over the x-axis, then moved it down, then moved it over, then you got lucky, yes.
So should you start with reflection first, regardless of whatever the operation?
Should it start with reflection first?
Let's say like,
That's not so much the issue. It's this right here can't be first. But the thing is, if we have a systematic way of approaching it, we should use it. And that's why the order of operations. Start from the inside, work your way out. If you follow that list, you should be okay. All right, well, shall we, we didn't look at any of these. We don't need to, right? There are some examples. I think we can handle that. Sketch this. Hold on. We do need to talk about those, but I'm just trying to see where we need to go with this. Okay. You want to try that one? Try D. See if you can do D. You should be done. You done? No, I'm kidding. Pardon? Anybody there yet? No? I'll draw mine on the board while y'all are working on it. There they are. Toolbox function, move to the right 4. 1/4 of it's going to vertically compress it or horizontally stretch, and then just move that whole thing up 5. Okay? That's it. All right, now things are going to get a little weirder now. All right, let's. What I didn't tell you last time is like why would you want to be able to do this quickly? Okay, let me write down this function. It was called J up there, but I'm calling it F. F of x is 1/4 square root of x minus 4 plus 5. All right. I need a volunteer. Okay. Is it possible for me to plug in a number right here and get out an answer of 2? Yeah, is there an x I can plug in and this will spit out 2? Why?
8.
Can anyone give me a definitive answer, yes or no, and explain why?
No, because it's not in the domain. It's not 4 to infinity, right?
Close, but I'm saying, is there an x I can plug in You're close. Anyone? No, don't erase it, or?
No, it's not, obviously.
Hmm?
Because you moved up 5 and then you only keep going up.
Okay, if I look at this right here, what's the range of that function?
5 to infinity.
5 to infinity. Everyone agree? 5 to infinity. That's the range? You can tell by just looking at that. That means, is it possible for 2 to ever come out of this? 3? 4? 5? Yes, 5 can come out, right? Can I plug 0 into this function? Can I plug 0 in?
Yes.
What's your domain? 4 to infinity. Right? Can you plug in 0 into this function? No. Look. Plug 0 in, what do you get? Square root negative 4. Oops, can't do that. What I'm trying to get you to see is that you can answer a lot of questions about this function that are difficult to do by looking at this, that are much easier to do by looking at this. Am I making any sense here? I mean, if you just go in there and you just ask someone, hey, look, I'm curious to see if, like, is it possible for me to plug in an x and it spits out 4.78? And someone's going to sit there, well, I don't know. I'm going to have to set that equal to 4.78 and try and solve it. But if you understand, now you know that
it's being moved up 5 and it goes up because you did the toolbox.
that's right. Oh, as long as you knew what that one looked like to begin with. Because if it were cube root, right, then that would be able to achieve that value. So as long as you're comfortable with it enough, you can answer the question pretty quickly. All I'm trying to do is tie some meaning into why we'd want to be able to graph something quickly. Because you can visually look at it and pick up a lot of information about its domain and range and so on. All right. This is a strange question. Suppose the x-intercepts of a graph are given. So here's what I'm telling you. The x-intercepts of a graph are given. Here they are. Ow, what the hell is that? There is a function that when you draw it, those are its x-intercepts. Okay? First question, A. What are the x-intercepts of f of x plus 4? So this is the graph of the function f. We actually don't even know what it looks like, do we? We don't. So I can make something up here. I could say it does this, and does this, and does this. It's a function, though, so it has to pass a vertical line test. That's what it's saying. It's a function. So this blue part is just something I made up. Well, all I know is that this point and this point cross through the x-axis. That's f, right? Tell me what the x-intercepts of f of x plus 4 are. So how are you getting that? So what does adding 4 inside the function do? Moves the whole thing to the left 4, doesn't it? So it takes this picture f and it moves it to the left 4. So that means it takes both these x-intercepts and moves them to the left 4. So just subtract 4 from each of those. So it would be, this is f moved left 4. So negative 12 and negative 3. Very good. How about the answer to part B? What are the x-intercepts of f of x minus 3?
Negative 8, or negative 5 and 4.
Okay, so that's really moving in the opposite direction, right?
Right.
So it's going to move it to the right. So we add 3 to both of those, negative 5 and 4. You all with me on that? What are the x-intercepts of 2x? Ooh.
Next is 8 and 1.
What? Negative 16 and 2?
Would it be negative 8 and 1? Yeah,
What does 2 do to it?
There's a vertical stretch.
2 inside is going to be some sort of compression or stretching, right? If this point is 0, how do you stretch 0? You don't, do you? How do you compress 0? You don't. Therefore, it doesn't move. Understand? It doesn't move at all. I don't know if you remember when we did the absolute value function, of course when we moved it up, down, left, right, things moved, right? But when we stretched it vertically, remember that that point always stayed there? It did this, or when we did it the other way, it did this, right? But notice that base point, that x-intercept never moved when we tried to stretch it. And so when you have x-intercepts and you stretch, right, it's like pulling this part down and pushing this part up, this part down, this part up. But these anchor points never move because they're 0. Yeah.
It would be the same basic explanation for the last one, for f of negative x.
That's going to be a little different. So C, what do we say? Negative 8, 1? What does, oh, did we talk about what a negative inside is? I think I skipped over that on accident.
We talked about on the outside.
Right here. Yeah, a negative on the outside reflected over the x-axis. A negative on the inside is the y-axis. Sorry, I forgot to mention that. Oops. So if you take this picture and you reflect the whole picture over the y-axis, that means everything that was here flips over there, and everything that's here flips over here. So this x-intercept now comes over here to become 8, and this one flips over to become negative 1. So for this part, you get negative 1 and 8. Yeah? Questions? Let's look at the next example. Given this graph of f, graph the following. So I'm going to go up to the board to do this one. Make this a little bigger. Make this a little smaller. I think I can do that. Yes. All right, so let me get up there on the board. Let's do part A. So the graph is given. Here's f. What is f of x plus 1?
You move the entire thing upward.
Move the whole thing up 1. Do I need to draw that? No. Okay, just the whole thing goes up 1. All right, how about f of x plus 2? Whole thing moves left 2. So just grab each point 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, and then just draw that shape again, right? Negative f of x.
Reflect over the x-axis.
Reflected over the x-axis. What would that look like?
Negative.
So that goes and becomes negative 3, right? Let's see, this one here comes up to here. This one comes up to here. And you could do this for all these points, right? You could just like measure this out and come up here and do that. And the x-intercepts don't move, do they? So something like that. That would be negative f of x. This one would be left 1, down 2. So move the black one over left 1, down 2. Half. Compression, vertical compression or horizontal stretch. It's halving every value, every y value, right? So I'll do this one in red. That means at 0 it was 3. At negative 2 it's 0, so half of that's still 0, so that still stays. Same sort of thing on this side. And then over here, this is negative 3, half of that's negative 3 halves, and over here, same thing. And then we just get like this miniature curve like this. That would be half of f. F of negative x.
Reflect over the y?
Reflect over y. So it's actually itself, isn't it?
Yep.
It would be itself?
Or we assume without actually having seen the function itself. Yeah.
Well, it looks like I've stopped it, right? So it looks like it's a perfect mirror image of. Okay. That pretty clear? You just want me to give you a bunch of those on the test? That's it. Call it a day. All right. Okay. Okay, we have, can someone erase that? Is there an eraser over there? Here. If you don't mind. There, thank you. Actually, would you mind just taking it the rest of the way? I got some stuff I need to do. No? Okay. Okay, graph these functions using completing of the square. How many of you have heard of completing of the square? When did you use complete? Well, hold on, let's show hands again. Completing the square. Okay, so some of you, okay. When did you use completing the square? Does anyone remember?
Oh,
When you were factoring, right? And you used it to actually solve quadratic equations.
Yeah.
Yes? You remember this? Some of you, I know you don't, but okay, so if you've used completing in the square in the past, what I'm about to talk about is extremely important. Even if you understood completing the square, even if you did, you need to pay attention because we've got a problem, right? We have a little bit of an issue. So let's just recall what it was. So I'm not even going to look at that problem up there. I'm just going to write that quadratic up there. X squared plus 4x plus 2. If I had come in here and said, hey, let's set that equal to 0, everyone, and I said solve this, how would you go about trying to solve this? This was on that take-home assessment. Something like that was on the take-home assessment. You try and factor this, not going to happen. So what do you fall back on when nothing else works with the quadratic equation? The quadratic formula, right?
Yeah.
The negative b plus or minus square root b squared. That always worked, right? That always worked. But you could also use completing of the square.
That takes long.
It takes longer. It's much more tedious. Much more tedious. But it works. And it's a skill that everyone in this class needs to know how to use it, how to do it. And the reason why is not only because you want to be able to solve that, but also because we want to be able to do what we're going to be doing here. And trust me, in calculus, and Cal 1, 2, and 3, you have to be able to complete the square. So if it's this thing that you've wanted to avoid your whole life because you don't like it, you have no choice other than changing your major. That you've got to, if you're going to take more math, you're going to have to be able to complete the square. There's no way around it. But there's a proper way to do it, and there's a dangerous way to do it. So I'm curious to see how you learned it. All right, here we go. Anyone who remembers it, tell me what I need to do first.
So yeah, subtract 2.
Subtract 2 from both sides. Okay. How many of you agree that that could be done here? Okay, so you would subtract 2 from both sides. And what I'm going to do is next to this, I'm going to put a red little mark on the side every time I think what you're doing is correct but dangerous. Okay, that is correct but dangerous. Here we go. I'll come back and tell you why in a second. What's the next thing after you do that?
Factor out an x.
Not for completing of the square. No. Okay, so this is where you have to look at the number in front of x. You take half of it. Always. Do you remember that part? Take half of x. But before you can do that, what must the number in front of the x squared be? A 1. Okay, so you have to check. Do I have a 1 out here? Yes. Okay, now I take the 4 right here. I'm going to write it down over here. I take it and divide it by 2. What is that number? 2. Okay? I'm going to put a little star next to this. This is my first little magic number in completing of the square. Once I get this little magic number, I take that number and do what with it? Anyone? So you remember the half part. That's good. Half of the 4 is 2. You square it. Yes, you square it. And you get 4. And that's my second little magic number. Is this ringing a bell? No? Anyone remember what to do with the 4?
You plug it into both sides.
You add it to both sides. Yeah? Y'all remember that? So you take it and you add 4 to both sides. Now you're allowed to do that because you have an equation, don't you? You can always add something to both sides? Yes? Yeah, that's very dangerous, and you'll see why in a little while. It's not dangerous, but it's going to get you into trouble later, in a later class. It's all mathematically correct. There's nothing wrong with this. That's why it's a check mark, but it's just... Okay, so this is the standard procedure for completing the square. You make sure there's a 1 in front of x squared. You take that number, you half it, always half it. Keep that on the side. Take that number, square it for that number you add to both sides. Here we go. Now, what are you guaranteed, those of you who said you understood this, what are you guaranteed about these 3 guys right here? What's guaranteed? They're going to factor into what we call a perfect square trinomial. It'll guaranteed be x and then plus or minus a number squared. In this case, plus 2. Actually, that comes from this number. That's positive 2. That's the number that goes here. And then the right side of the equation becomes 2, right? Negative 2 plus 4. Y'all okay with this? And now at this point, what would you do to solve for x? Square root both sides. So you'd square root the left side. And when you square root the right side, you have to do plus or minus root 2. The left side becomes what? X plus 2 equals plus or minus root 2. And then finally, to get x, subtract 2 on both sides. So x is negative 2 plus or minus root 2. Those are your 2 solutions. Now, if you would have done the quadratic formula instead, you would have got the same thing. I'll show you that real quick right here. Quadratic formula on this. Negative b, which is negative 4, plus or minus the square root. B squared is 16 minus 4 times what's a? 1 times c, 2, so 4 times 2 all over 2a, so 2 times 1. And that would become, let's see, 16 minus 8 is 8. So we have negative 4 plus or minus root 8 all over 2. How can you rewrite root 8? 4 times 2, and then take out a square root of 4, which would be negative 4 plus or minus 2 root 2 all over 2. And then 2, that's a 1, this is a 2. And you get negative 2 plus or minus 1 root 2, and then over 1. So this is the same answer, right? What's faster? The quadratic formula is much faster, isn't it? But it's the technique of completing the square that everyone needs to be comfortable with. And this way, although correct, has 2 dangerous spots. Okay? All right, so I'm gonna fix this for you, okay? I'm gonna fix it. I'm gonna show you the right way to do it. But are there any questions? Let's go to this. Let's look at this example. The example says, look at this function and complete the square and then use transformations to graph it. So they're giving you this function f of x is x squared plus 4x plus 2. What I need to do is complete the square and then use transformations. So we know that by what I just showed you, that when you do completing of the square properly, you get something like x, I don't know, we had plus 2, right? Squared and then numbers and stuff. I don't know what it's going to turn out to be, but maybe it's like plus 3. If I asked you to graph that, could you graph that? What's the toolbox function? Squared. What has it done? We've moved it left 2 and up 3, right? So we can somehow just turn this into this. We could graph it easily, couldn't we? So let's try and turn that into something like this. So we will complete the square to do that. Does anyone see the first problem, the first issue? It's not set to 0. This is not an equation. And this is the problem you run into in Cal 1 and Cal 2 and in Cal 3, is that if you don't have an equation, you can't do that first step of moving that stuff to the other side because there is no other side. So what I have to do is look at this instead as an expression, not an equation, and still complete the square. So how in the hell do I do that? Well, here's how you do it. I'm still going to make sure that I have a 1 here, which I do, right? Okay, so I've got a 1. I'm going to write it here just to kind of stress to you that it's there. This equals, so that equals this. And then I'm still going to take that number 4. I'm still going to divide it by 2. That's going to give me 2. That's still going to be a magic number for me. I'm going to take that number, I'm still going to square it, which is going to give me 4. That's still going to be a special number, right? But here's the deal. I can't add 4 to both sides because I have no both sides, right? So what I'm going to do is I'm going to realize this is one of the first times this is going to ever happen to you. So enjoy it. You're about to see something you probably haven't seen before. You're going to realize that right there is a 0. We call that a hidden 0. And now we've used hidden things before, like anytime we've wanted to do like something like this, and we wanted to put these together, right? We get a common denominator. And we, like for this one, we would multiply the top and bottom here by what? To get x plus 3, and then over here we would do what? X on top and bottom. These were little hidden whats.
Numbers?
Yes, but what is something over itself? It's 1, right? This is like a hidden 1, isn't it? Like sitting next to everything, we realize that there's times 1. Anything times 1 is itself. So we've used hidden 1s throughout our entire mathematical lives. What we have not done a lot of, in fact, most of you probably have never done, is realize that sitting next to everything is not times 0, but plus 0. This is a hidden 0, and this is a much more advanced concept in mathematics, to realize hidden zeros. Some of the toughest theorems that are used in Calculus 1, some of the toughest theorems and formulas that we get in that class, to prove that they're true, you have to realize hidden zeros. It's interesting. And who are math majors? Any math majors? No? Okay. Well, then you don't get to realize a whole lot of hidden zeros. But this one's important. Guess what that hidden 0 is going to be?
0.
It is going to be 0, but I'm going to write it a different way.
On the other side?
What did I want to do with this? Didn't I want to have an add 4 to both sides of the equation, but I don't have both sides of the equation? So how can I still add 4 without actually adding 4? Add 4 and
0.
and subtract 4. And you're going to think I'm crazy, aren't you? Here it is. I'm going to add 4 and subtract 4. Everyone agree that what's in red is still 0? And what's still there? 2 plus 2. I haven't changed the problem, have I? I've just used the fact that there is a 0 sitting next to everything. And now, what are you guaranteeing these first 3 will factor to be? X plus 2 squared, right? X plus 2 squared. So that becomes equal to x plus 2, that quantity squared. But what's still left out there? This right here. These two together, right? You have to put that negative 4 back together with that 2, so you get negative 2. That you can graph, can't you? This is a parabola that's what? Move to the left 2 and down 2. And you graph it.
And I'm just so like mind blown on the fact that we've been multiplying things by 1. Is that
That whole time, that's what you've been doing? Yeah. We've always been coming in with that little 1. And it's helped us out quite a bit, right? All right, so this is the proper way to complete the square. Now, if you have an equation, feel free to stick to the way you've been doing it. But I still think this is more valuable if you learn how to do it this way, especially on the next one. Let's do this last one. Do I have time? Yes. Look at this last one. This is kind of like the ultimate whammy here. Negative 3x squared plus 6x plus 1. Same instructions. Go ahead and complete the square on it. And once you've completed the square, you graph. So do you see we have a problem already to start?
It's not equal to 0.
It's not equal to 0. And we have a negative 3 in front of x squared, and we just said that you had to have a 1. So how am I going to get that negative 3 out of there?
You divide by negative 3?
If it were an equation, that's what we'd do, right? We'd divide by negative 3. But it's not. It's an expression. So you can't just like divide through an expression by negative 3 and still have the same thing. So I'm just going to be a little clever here, because that's what math people and engineers have to be, is clever. I'm factoring out a negative 3. I'm allowed to do that? As long as when I push it back through the parentheses, I have what I started with. So when I pass this back here, do I get this? Yeah? If I do negative 3 times negative 2, I get positive 6. I get that, x. And if I do negative 3 times negative 1/3, do I get positive 1? Yes. So do you see what I've done there? Still completely okay. I'm like, I haven't broken any algebra rules here. Now what I'm going to do is I'm just going to focus all my attention right here and act like that was the problem given to me and that there's a 1 in front, right? So if this is a 1 now in front, we're going to look at this number, negative 2, and take half of it, which is negative 1. That's one of my special numbers. And then the other one is square it, which is 1. That's my second special number right there. Any questions? Go ahead.
The negative.
Negative 1. You're taking negative 2 and you're halving it. So negative 1. Yes?
Okay, so what purpose, like, I'm still kind of confused. What purpose do those first and second numbers that you're getting do for you? Like that negative 1 and that 1?
Okay, this number is going to be what I use for my hidden 0. Okay, like in the last problem I had a 4 here, right? So I added 4 and subtracted 4.
This one you're going to add 1.
Add and subtract 1. This number is what's going to be in the parentheses with the x, the square thing. I should do it this way. X, and then it'll be minus 1, that quantity squared. You'll see it when I do the next step.
Just skip that step?
What's that?
Can we just skip that step and go straight to x1?
I would be real careful. You'll see, because the negative 3, I'm just concerned about the negative 3 and how you would treat that. So maybe, but look, if this is negative 3, right? Here's a set of parentheses. I'm going to realize my hidden 0 right here behind this 2x is where my hidden 0 is going to be. So right in here is where I had plus 0, right? So I'm going to write down x squared minus 2x, but my hidden 0 I'm going to write in here using this number, which is going to be plus 1 minus 1. Do not do minus 1 plus 1. It's plus 1 minus 1.
Are you always going to do plus than
Yes, always plus than minus
Okay.
for completing of the square.
Yeah.
And then what's still in there next to this? Minus 1/3. Like that, right? Now, I had more markers, other colors. I'm guaranteed that the first 3 terms are going to be a perfect square trinomial, right? This right here, these 3 are going to be a perfect square trinomial. And they will be, this is the number that's going to dictate what's in that parentheses. So just this in blue is x minus 1, got it? Squared. Now what's still in here?
The negative
Negative 1, take away 1/3, negative 4/3, right? But doesn't that all still live inside this parentheses with the negative 3 in front? Do you see the thing that I thought might be dangerous there? I don't know if you would have picked up the negative 4/3. Maybe you're okay with that, I don't know. Now, I need to get rid of the parentheses. So I'm going to distribute negative 3 back through. I've got to multiply it here, and I've got to multiply it here. So let's talk about multiplying it times this. Can the negative 3 go inside of this? No, because you've got to do squaring before you can multiply, right? So it's just going to sit out in front of it. Negative 3 sitting in front of x minus 1 squared. Then you're going to do negative 3 times negative 4/3. What will happen there? Negative 3 times negative 4/3. It's going to be a positive, right? Positive what? 4. That's it. It's a parabola, right? Squaring function. It's been moved to the right one. It's been stretched vertically. It's been flipped over the x-axis. It's been moved up 4. Got the idea? You learned something today. You have a question?
How did you get 4/3?
How did I get 4/3? Oh, right here. Remember that minus 1 that came off of the plus 1 minus 1? I'm just doing negative 1, take away a third. All right, so you have to get a common denominator. Negative 3/3 minus 1/3. So you just turn negative 1 into negative 3 over 3. And then just put them together. Yeah? All right, sign-in sheet went around. Yes? Who needs to sign in? I think we're good. I'll see you on next time we meet, Thursday. Yes. Let me turn off the video.